In this video today, we are going to look at the cause of refraction, or what causes refraction of light. But before we proceed, again a reminder, whenever we draw pictures for be it refraction or reflection of light, remember we should not forget to draw the arrowhead. Alright, the arrowhead shows us from which direction the ray of light is coming or towards which direction the ray of light is going. Okay, so it is very, very important that you show the arrowhead. If you do not show the arrowhead, okay, you have everything correct except that you haven't shown the arrowhead, then you do not get marks, remember that. So it's very, very important to show the arrowhead. Do not forget that. So let us start with the cause of refraction of light. Remember, it is the change in speed of light when light travels from one medium to another that causes refraction of light. Say, for example, a ray of light is moving from a rarer to a denser medium. Okay, what happens is, compared to this rarer medium, the denser medium will offer more opposition or resistance to the movement of light. Light simply wants to pass through these media. Okay, light media, of course, is the plural of medium, don't forget. So light wants to pass through this medium. All right, so to this passage of light, what happens is the medium always offers, whatever kind of medium it be, the medium always offers some resistance or opposition to the passage of light. And only thing is, compared to the rarer medium, the denser medium always offers more resistance or opposition to the movement of light, simply because the denser medium has more density. That is why it is called the denser medium. Alright, so rarer medium has lesser density, okay, so to say lesser molecules close together, so light can easily pass through it. Whereas the denser medium has more density, that is more molecules close together, okay, so it is difficult for the light to pass through. Alright, so therefore what happens is the speed of light changes when it moves from one medium to another. So to say, when ray of light moves from rarer medium to denser medium, the speed of light slows down. Okay, alright, so this change in the speed of light is what causes refraction of light. And exactly the reverse happens, okay, when light moves from denser medium to rarer medium. Here it is difficult for the light to pass through, okay, so it is moving slowly. But the moment it enters the rarer medium, what happens is it becomes more easy for the light to move, to pass through. Alright, so therefore it moves very fast through the rarer medium. So there's a change in speed, okay, whenever a ray of light moves from one medium to another. And it is this change in speed which causes bending of light. Okay, to add to that, since the denser medium offers more resistance, opposition, okay, so therefore this ray of light wants to get out of this denser medium as soon as possible. Okay, the denser medium is like a very crowded corridor, overcrowded corridor. All right, so you have to pass through this corridor, and through this overcrowded corridor, of course, you would like to get out of it as soon as possible, quickly. Alright, so therefore, since light also wants to get out of this denser medium, overcrowded corridor as soon as possible, so therefore it bends towards the normal. Okay, because it wants to kind of take a shorter route over here. Okay, say for example, the thickness of the denser medium is this much. So this would be the shorter route for the light to take, so therefore it bends towards the normal. Whereas when light moves from denser to rarer medium, what happens is this rarer medium is offering lesser resistance. Okay, alright, so it's a very easy going path. So it does not matter to light if it takes a longer route also. Alright, that is why it bends away from the normal. Therefore, remember, it is this change in speed of light whenever it moves from one medium to another that causes bending of light or refraction of light. Now another thing that you need to remember is this thing, that is the value of the speed of light in error vacuum. The speed of light in error vacuum is 3 into 10 to the power 8 meters per second. Now this is a very, very high value of speed. Okay, this is also equal to 3 lakh kilometers per second. So you can see light travels 3 lakh kilometers in 1 second. Okay, so this is a very, very high value of speed, and you need to remember this value. With that, we move to another definition of refractive index. But before we looked at this definition, let us give a look at the definition that we learned in the previous video, which is this. So refractive index of the second medium with respect to the first is the ratio of the sine of angle of incidence in the first medium to the sine of angle of refraction in the second medium. Since light travels with different speeds, okay, so therefore the speed of light in the first medium divided by the speed of light in the second medium also gives us the value of refractive index of the second medium with respect to the first medium. Okay, so with that, let us look at this relation. Remember, light is a wave. Okay, light is an electromagnetic wave which is transverse in nature. Okay, now a transverse wave looks like this. Alright, so light is an electromagnetic wave which is transverse in nature, whereas sound, we are going to discuss about sound in detail, okay, in the classes to follow. So sound, remember, is a mechanical wave which is longitudinal in nature. Okay, so this length is what is called the wavelength. The length of one complete wave is what is called a wavelength, remember, denoted by a Greek letter lambda. Now for any wave, be it electromagnetic wave, be it mechanical wave, or be it transverse in nature, be it longitudinal in nature, remember, for any wave will have three characteristic properties. Okay, one is any wave will have a certain velocity. Any wave will be moving with a certain speed or velocity. Any wave will have a wavelength. Okay, and any wave will have a frequency. Okay, the relation between them being given by this relation between velocity, frequency, and wavelength, of course that of a wave, is this: v is equal to n lambda, where v is the velocity of the wave, n is the frequency of the wave, lambda is of course the wavelength. So understand one thing very clearly now, and that is, whenever refraction takes place, okay, what happens is the speed of light we are seeing changes. So whenever the speed of light changes, when it moves from one medium to another, there has to be either a change in frequency of light, or a change in wavelength of light, or a change in both. Since there is a change in speed happening, there has to be either a change in this n, or a change in lambda, or a change in both. But what we see is, whenever refraction happens, remember, there is no change in the frequency of light. Okay, so since there is no change in frequency, there has to be a change in wavelength of light. Alright, so remember, whenever light moves from one medium to another, the speed of light changes, thereby the wavelength of light changes, whereas the frequency of light does not change. Sometimes you get a question like, which property of light does not change when it moves from one medium to another? Okay, and why? Okay, the answer of course is frequency, and the reason being, frequency of light depends on the source from which it is coming. Okay, so it is the source of light which determines what will be the frequency of that light. Therefore, there is no change in frequency of light whenever it moves from one medium to another, since frequency is dependent on the source of light. Remember that. This brings us to the third definition of refractive index. Okay, see, this was the second definition of refractive index. Refractive index of the second medium with respect to the first medium is speed of light in first medium, we are calling it v1, divided by speed of light in second medium, we are calling it v2. So mu21 is v1 upon v2. Now since velocity is frequency into wavelength, so v1 can be written as n into lambda 1, and v2 is n into lambda 2. It's the same light passing from one medium to another, so therefore the frequency doesn't change. Okay, so n and n, they divide each other out, so therefore we get refractive index of the second medium with respect to the first to be equal to lambda 1 upon lambda 2. That is the third definition for refractive index. Refractive index of the second medium with respect to the first medium is the ratio of the wavelength of light in the first medium to the wavelength of light in the second medium. Okay, so I have written the three definitions of refractive index over here. So remember these three definitions of refractive index, that of the second medium with respect to the first. And finally, in this video, let us talk about the conditions for a ray of light to travel undeviated. In what cases, light moves undeviated whenever it moves from one medium to another. This first case, we've already discussed this actually. Okay, that is whenever light travels from one medium to another at an angle, being incident at an angle of 0 degrees, that is for normal incidence. Whenever the ray of light is incident normally to the surface of separation between the two media, remember the ray of light travels undeviated in this case. So this is condition number 1. And condition number 2, if we have two different transparent media having the same value of refractive index. Okay, so when the refractive index of the second medium is the same as that of the first medium, okay, then also the ray of light travels undeviated. Okay, because both of these two media, medium number 1 and medium number 2, both of these two media, they offer the same resistance to the movement of light. So therefore there is no question of light bending. Okay, so these are the two conditions for a ray of light to travel undeviated.